Today's program is being recorded. Any views expressed in this webinar are for general educational purposes only and do not represent any official views or positions of the sponsoring or presenters organizations. We are looking forward to your questions at the end of the program, so please continue to send them using the Q&A section. Greetings and welcome to today's educational program in the webinar series of Preparing for Process Analysis number 8, Using Analysis of Variance for Fun and Profit by Sandy Furterer and Doug Wood. This is your moderator, Shobha Mittal with ASQ Quality Management Division. Today we have the distinct pleasure of hearing from Sandy and Doug. Please join me in welcoming them. Dr. Sandy Furterer is a professor of practice at The Ohio State University in the Department of Integrated System Engineering. She has applied Lean Six Sigma, systems engineering, and engineering management tools in healthcare and other service industries. She previously managed the Enterprise Performance Excellence Center in a healthcare system. Dr. Furterer received her PhD in industrial engineering with a specialization in quality engineering from the University of Central Florida in 2004. She received an MBA from Xavier's University and a bachelor's and a master's of science in industrial and systems engineering from the Ohio State University. Dr. Furterer has over 25 years of experience in business process and quality improvements. She is an ASQ certified Six Sigma Black Belt, certified manager of quality and organizational excellence, certified quality engineer, an ASQ fellow, and a certified Six Sigma Master Black Belt. Dr. Furterer is also an author and co-author of several academic journal articles, conference proceedings, and 9 reference book textbooks. She co-edited the ASQ CQIA handbook and the ASQ CMQOE handbook, and is the editor of the ASQ CQPA handbook. She also published a textbook on systems engineering, holistic life cycle architecture, modeling and design with real world application, CRC Press 2021. I will now introduce Doug. Mr. Doug Wood has worked over 40 years in the areas of cost of quality, office waste, root cause analysis, performance measurement, etc. He has helped others with various ASQ certifications in quality auditing, management, and engineering. He has also taught audit, Lean Six Sigma, cost of quality, statistics, and failure modes and effect analysis. He has 4 ASQ certifications, CQE, CQA, SSBB, and CMQOE. Doug was the recipient of 2023 ASQ Quality Management Division Howard Jones Award and was given for outstanding long-term service as a Vice Chair for Education from 2015 to 2021. Doug has 3 publications by ASQ: The Certified Manager of Quality Organizational Excellence Handbook 5th edition, co-edited by Sandy also. The Executive Guide to Understanding and Implementing Quality Cost Programs, Reduce Operating Expense and Increasing Revenue. Principles of Quality Cost, Financial Measures for Strategic Implementation of Quality Management, 4th edition. His firm, DC Wood Consulting LLC, has worked with clients in manufacturing, healthcare, and transactional businesses. His company website is www.dcwoodconsulting.com. And so, without further ado, it is my absolute pleasure to introduce Sandy and Doug to you all. The floor is yours.
Thank you. All right. So thanks everybody for being here. We've got quite a few attendees. It's wonderful to share our knowledge on this topic with you. We didn't know if there'd be a lot of people for something as technical as ANOVA, but it's great to see all of you. So I'm going to share the PowerPoint here, and let me go ahead and put this into slideshow. You might notice that is not a Teletubby behind me. That is Brutus Buckeye. So just so you know, Doug thought it was a Teletubby, but anyway, we'll forgive him that, not knowing Brutus. Guy from Kansas. Okay, so I'm going to start off with the presentation, and I'm going to talk about analysis of variance, the different types, the different models that you can use, some of the assumptions, how it compares to hypothesis testing, where that comes in. And then I'm going to go through an example of an analysis of variance. I think that that is the best way to learn, to really understand kind of a simple example, but kind of fun. And then where this would be used, the usual steps, and then common kinds of errors. Doug's going to cover those last three areas after the example. So, all right. So the analysis of variance, it's a statistical tool. And the difference between this and like a two-sample t-test or a z-test is that it is looking at multiple means or multiple distributions or multiple samples of data to compare the mean, but it uses the variance to do that. So we'll look at how that ends up happening. But when you get more than two distributions or two means, then you're going to increase your type 1 error by a lot if you just keep comparing pairs of means. So analysis of variance is a great tool to compare when you have multiple group means. And what it does, how it does that is it kind of carves up different sources of variation. It looks at the variation related to what you care about, what's happening with the treatment of different factors, treatments, and levels of those factors. And then it partitions out some error variance. And sometimes if you block where you say you have different machines and you want to kind of remove that nuisance variable, or you have different operators that are performing the experiments, then you can also have block variation as well. Analysis of variance is very useful because it can be used in a wide variety of the ways that we collect data and then compare it. So it's a really super robust tool. There are two basic types of models where we look at fixed effects. This is when we look at the treatment variables and we choose the levels. So it might be temperature. So say we're extruding a plastic cup through an oven across a die, and you have different temperatures in that oven. And you might have temperature of 150 degrees, and you might have temperature of 170 degrees. And you want to see which one gives you a better cup extrusion, better quality of the cup. And so that's an example of you are picking those values based on knowledge of your process. And one of the things I always tell my students, the most important thing when you're using analysis of variance and collecting data, doing designs of experiments, any of those types of techniques, knowledge of your process is absolutely key so that you can identify what is my response variable, what the dependent variable, and then what are my factors that I care about, that I want to try to understand better. And so you initially go in with some assumptions and hypotheses, and then you try to prove that out through the experimentation and the analysis. The other type of model is called a random effects model. That's where you select the factors randomly. Good example that we have here, operators. So you may have several operators performing this experiment or running product across a piece of equipment, and you want to control for that, and they call it a nuisance variable. And so you would set those, you would randomly select operators for the study. It could also be randomly select pieces of equipment. You've got 20 milling machines, and you select 3 of them as your factors. So the analysis typically is very similar, but it's important to know from a fixed versus a random effects whether you can extrapolate the results for the fixed effects versus random effects. Fixed effects, you're very specifically testing those fixed factor levels. Random effects, you should be able to extrapolate your results across all of those, the operators or the equipment or whatever it is. So again, I guess I'm a little ahead of myself. So I have an example that I'm going to use here. And my daughter likes to ice skate. And so I picked something that I thought might kind of interest her and maybe interest others out there. And so she tells me that the boots, the blades, the ice skates can be very expensive. And the better skater you are, the better skates you want, because these really do matter. So what I was imagining was that you've got an ice skate blade manufacturer and they're trying different materials. They're trying to get to this new type of ice skate blade. So they're going to compare 4 different material types in this ice skate. So you've got the factor as an ice skate with 4 different levels. So since you're specifically picking those 4 different types of material types and you're not randomly selecting them, you know exactly what those material types are and you selected them to study, then you cannot extend to other material types that you have not explicitly considered. So that's a fixed effects model. For the assumptions, you're going to assume that you have a normal distribution, and we can easily test that, and that the distributions are independently distributed random variables with mean, 0, and variance. And your variance is assumed to be constant for all levels of the factors, and of course you can also test that. Random effects model, the experimenter is going to pick the factor and levels randomly from a population. So if you have a population of equipment that you're interested in studying in the plant, that you're running some manufacturing process across the equipment, and you're randomly selecting the, four of those machines across the 20 that you have. And then you can extend, assuming that those machines are similar enough, those treatments that weren't explicit, those machines that weren't explicitly considered. And Doug, feel free to jump in if you have anything to add on any of these slides.
Sure, I'll do that.
Okay, yeah, and we always create these together. I was getting very busy lately, and Doug was getting very nervous that I wasn't providing my input to the slides, and I finally did that. It was pretty funny. I said, "Are you getting nervous, Doug?" He's been great through all these. He's wonderful. All right. So then we start with, usually when I'm teaching this class, with a one-way or a single factor analysis of variance. And you have one factor and it's varied at different levels. The important thing through all these experiments and data collection is that you run the experiments in random order. You can also test that through looking at your residuals, and we'll look at some examples here as well. So this is like this, using my ice skate blade example. They're going to try 4 different blade material types for the one factor, the blade. One factor, single factor, 4 different levels. So the analysis of variance hypotheses, we test, whereas if you had a 2-sample T, you would test if 2 means were equal to each other for the null hypothesis. We're testing in this example whether the 4 means are equal to each other. And that's our null hypothesis. Versus if we get enough support in our analysis to test to reject the null hypothesis, and we have our alternative hypothesis where at least one mean is not equal to the others. Now this is really critical because a lot of people think that with your analysis of variance, you're going to find out which mean is not equal, but through the actual analysis of variance table, you only find that there is at least one mean that's not equal to the others. There could be more. And then you have to perform a couple different kind of tests that help you to identify which means are not equal. So here is the sum of squares for the ANOVA table. And so what we do, we had talked earlier about partitioning our sum of squares, which is our variance. And so for this single factor, you have the total sum of squares, and which consists of your treatment variance and your error variance. Now this actually, it looks pretty complex, but it's actually very simple to even do this by hand, which I make my students also do so they have an appreciation of where this is coming from. And then we don't look back and we move forward with Minitab. So the sum of square treatments is taking the treatment mean, which is the y sub I, and it's a dot, which means each treatment mean, which is the first one. So it'd be y1, the average. It'd be the second material average responses, the third and the fourth. And we subtract each of those minus the overall grand mean, the mean of all of the observations together. And then we square each of those and add them together. So it's really pretty simple. We just take the mean. Go ahead.
So that's telling you how different are the 4 different averages for the skating blades from the average of the 4 together, right?
Yes, absolutely. Perfectly said. So then we can see whether we have a difference between those means by that formula. Then we have the sum of squared error. This helps us to calculate the deviations of each individual observation. So we've got that Yij subscript, and that means it's each. So if we have 4 treatment means and we have 5, we run it 5 times, 5 replicates each. And then we would have 20 different observations, and we would subtract each from each treatment mean. So we would have each individual blade, the observations within those 5 observations for each blade, subtracted off of the mean of that. So we're seeing the difference between each observation in that treatment, like blade 1, material 1, and we take the difference from the mean of that treatment. Does that make sense?
So this is variation within the type of blade, right?
Yep.
Okay.
Perfect. All right. Let me see. Go. All right. Then we have the total, and this is each individual observation again across all of them, so all 20, and subtract off the grand mean. So this is basically, if you look back, if I can look back, it's adding this treatment plus the error. Now, the nice thing about it is, since we've got this formula that sums them, we don't actually have to do the calculation of each. We can do these 2, and then we have the total, or we can do the treatment and subtract that from the total, whichever way you want to do it. So then this is our table, our analysis of variance table. This is ultimately what we're looking at to see if we have a difference in means. So they first have the source of variation. So we broke up the variation into different sources, different types. We have the treatment, the error, and the total. And so we've got the sum of squares, which is just the variance here for the treatment, the error, and the total. And we have the degrees of freedom. A signifies the number of factor levels. So in this case, we have the 4 factor levels, -1. N is the total number of observations. So if we had a total of 4 factor levels and 5 replicates each, we'd have 20. 20 minus the 4 would be 16. And then the total of degrees of freedom, we have the 20 minus 1, or 19 in that case. So this helps us to be able to calculate our mean square error, and then the mean square, because we take the sum of square treatment, divide by that degree of freedom, the sum of square error, divide by that degree of freedom, And then we divide the mean square of treatment divided by the mean square error, and we get what's called our F statistic, which we compare to a table value or calculate the probability of that occurring.
Oh, Sandy, so degrees of freedom is often a confusing term. Can you explain what it's doing here? I mean,
Yeah.
how it adds to the analysis.
So it helps us with not only in the pure calculation of the mean square, but it's also helping us to remove some of the bias in our calculations, and for us to partition out again those observations. Does that make sense? You might talk a
Yeah.
little bit more about that in the
So
last
so
one.
the MS column here, you're dividing these sums by a number, which is going to make it smaller, right? And comparing the two different degrees of freedom, A minus one and N minus A, that gives us a sense of how the different, how all the different treatments are varying, but it magnifies a little bit, doesn't it? The differences between them.
Mm-hmm. Mm-hmm. Yeah. Yeah. So then the other element too is you're getting a ratio of those variances. And
Mhm.
so if you don't have a difference between the treatment and the error, that would mean that that was close to 1. The farther that F value's from 1 with those degrees of freedom, the more chance you have that those variances are different and that the treatments really had an effect.
Okay, yeah, now that helps.
Okay, thank you. All right, so these cute little ice skates. So this is my example. The ice skate blade manufacturer, again, testing 4 different types of materials, and their response variable, the variable that they're going to assess whether there's a difference in, provides the best jumps and spins combined for a women's free skate program, one of the competitions. They measured the number of complete jumps and spins during the practices for the free skate program with each of 4 blade types. Now, I happened to look this up, and actually the women's national champion, or the national championships are going to be in Columbus this January, Ohio.
Ooh.
Very exciting.
Yeah.
Yes, got my tickets already. Anyway, and so we just imagine, again, this is a hypothetical. I don't think anybody's actually done this that I know of. It's my made up story. But we've got, I think there's about 14 required jumps and spins in the women's free skate program. So that's kind of a guideline. And so we're assuming that the better the blade, the better they're able to complete all these very difficult jumps and spins. We're using a 95% confidence interval, and that's about in the middle. It's not too stringent. It's just kind of in the middle.
So
And
there's a 5% chance that your study is not actually seeing what's going on, right?
let's see.
That it's inaccurate to reality.
Right.
Okay.
Right. Yeah. So then we can also test the assumption of normality. Oh, that's supposed to be normality and independence of the distributed random variables.
Mhm.
All right, so here's my supposed data. Remember, 14 is like these world-class skaters. So we've got number of spins and jumps completed total for our response variable. We've got 1 factor, 4 levels, 4 different blade types, and we have 5 replicates. So we've got these values. So we first want to test our assumptions. We test the null hypothesis that the distribution's normal, and the alternative is that the distribution's not normal for the distributions. And then we always use this to remember if P is low, our P value right here, the 0.418, then HO must go, meaning we reject the null hypothesis and conclude the distribution's not normal. So in this case, we don't really want to reject, we want a normal distribution. So it just so happens we have a normal distribution, 0.418 greater than 0.05. So we fail to reject. Go ahead.
On this probability plot, if the dots fall on the line, it's normal.
Mm-hmm.
It's a normal curve. Okay.
Yep. So if you have dots that are really far away or that look really weird or non-random, then you know you probably have a problem, and then you get into a whole bunch of other statistics way beyond this.
Yeah.
All right. And then the test for randomness, here's our normal probability plot up in the left again. This is versus the fit, the model that we're trying to fit. It tries to fit a line. And then we've got a histogram, which shows if you put a kind of a bell curve over that, looks pretty good. And these are our residuals from 0. And then you always plot to make sure that you ran this in a random order. So again, I told you we could check that. We want to do that, but we could also check whether somebody actually, you walk away and somebody may not run it randomly. So there you go. That looks pretty random, bounces up and down across the 0 line for the residuals. So we're okay. No non-random patterns here.
Okay.
So that was testing our assumptions. So now, I said this was actually pretty easy. This is our sum of square treatments. We take each of the averages here, and this is in Excel. We've got, again, our observations. We sum those up. We get a grand average across all of the observations as 7.7. We have an average of each of the blade types here, which is the Y sub 1 bar is 10, Y sub 2 bar is 8.8, 6.8 is Y sub 3 bar, and Y sub 4 bar is 5.0. The treatment average, the 10 minus the grand average, 7.7 is 2.4. The 8.8 minus 7.7 is 1.2, and so on. And then we square those and add them together and get our 14.59. We have a number of replicates of 5, and we get the sum of square treatments of 72.95.
So that's just 5 times the 14.59, right?
Correct. Yeah.
Okay.
That's the n right here.
That's the n. Okay, got it.
The number of n is actually the number of replicates, 5, not the number of A treatment levels.
Good.
All right. Now we take each of these individual observations and subtract it from the treatment mean. So we take 11 minus 10, 11 minus 10. We've got the 1. We got the 11 minus 10, a 1 again, 8 minus 10. Oh, I'm sorry. And then square it. 8 minus 10, 2 squared, and then the 9 minus 1. And these are all squared. So squared observation minus treatment average. So this is 8 minus 8.8 minus 0.8 squared, again, because we went the squared or without a sign kind of thing. So we do all of those, we add each of those, and then we sum those up. So all of those individually squared and then sum those up.
Okay.
Okay, and then just to show you, we could just add those two together to get a 97.6 plus a 72.95 is 170.5, but we could also prove this out and take each individual value, subtract it off from the grand mean, the 7.7, square those, add them up.
Either way, you come up with the same total, SST.
Right. So when you hear analysis of variance and of course statistics, you think, wow, this is really complex. I could never do this by hand. This was pretty simple to do by hand, really. So then we put these into our analysis of variance table. We have our 3 degrees of freedom for blade type, 4 different types of blades minus 3. Our error was the what was it? The 20 the 20 observations minus the 4 treatments. And then the total is the total 20 minus the 1.
Mhm.
Then we had our treatment, our 72.95 that we calculated, 97.6, and the total 170.55. Take 72.95 divided by 3, we get 24.317. 97.6 divided by 16 is 6.1. Our F value is 24.317 over 6.1. We'll let Minitab calculate our P value of 0.027 for the F value of 3.99. And see, this is a lot larger than 1 if those ratios were the same. The sum of squares, so the treatment is larger. And so we suspect that there is at least one mean that is different than the others. And that shows that where we say if P is low, below 0.05 for our significance level. So we reject HO, and we conclude that there's at least one mean that is not equal to the others.
Okay.
Then I told you there was another test. I'm going to use Tukey. There's also Fisher. There are two probably the most common statistical tests. So now I want to know, well, which one is different? So this calculates the means, and we already calculated this. Blade type 1, 10, blade type 2, 8.8, 3 is 6.8, and 4 is 5. And then you have the confidence interval, standard deviation there. And then this is really nice because what this helps us with is to see that if your confidence interval here for the difference between the means of the different treatment combinations do not cross this green line at 0, then that means those are the ones that are different. So we have the only one that shows that is different is 1 to 4. So that means 10 is statistically significantly different than 5.
So if the spread of this confidence interval is too large, it means you don't have enough samples, right?
Or your variance is large.
Yeah. Okay.
Yep. Either one.
Okay.
Yeah. All right. And then I think, Doug, this is you.
Oh, yeah.
You're jumping in
Okay.
now?
Yeah. All right. So, where can you do this? Well, it's used in quality control and manufacturing, especially when you've got different production processes, or there's a factor that significantly affects the quality of the product. Now, we all know what the 7 M's are, right? Material, machine, method, manpower, environment, or Mother Earth. Those are all sources of different factors, and you would choose the one that you think is most important. This gets back to Sandy's point about knowing your process, right? So you pick the one that you think is really going to be important. Now, Sandy, if I had 3 factors and I wanted to look at all of them at once, that would be not a single factor analysis of variance. That would be a multi-factor analysis of variance, right? Okay, so of course the expense goes up because you got more samples to run. All right, so that's how it's used in many manufacturing. Let's move on. What's the next one here? We're going to take a look at in agriculture. Now, a lot of people think, agriculture is all about dirt. Well, it's not. Agriculture has some of the most sophisticated statistics involved that you can possibly imagine. Many of our statistics were developed for agricultural purposes. Again, you've got different fertilizers, different irrigation methods, different seed types, different time of planting, and of course, there are random variables, rainfall, things like that, which interfere. But you're trying to look through the random variables and see what your controlled factors do, okay, on the result. So that's where it's used in agriculture. Next, please. customer satisfaction. Now, this is an interesting one. I mean, we have different regions or different customer segments. You know, you probably heard, well, you have to segment your customers. You've got to put your customers into categories, and you've got to look at what they're buying and what their interests are, and so on and so forth. Well, so what? What is there a difference between, you know, men and women buying your product? Is there a difference? Is there a difference between older and younger customers? Is there a difference between, if you're in business to business, is there a difference in the customer satisfaction between different kinds of clients? Okay, so it can be used in the same way to figure out what's significant in this thing. And otherwise you might not know. So the main steps here, okay? You need to define the problem. This is talking to management, discussing with the leaders. What's the problem? And that includes, what are the factors? What do we want to know? Where are we going with all of this? That has to be done, planned out beforehand. Then you sit down and you choose a response variable. Now, in our case, for the example, that was a number of jumps completed, okay? You know, an alternative thing in a skiing or in an ice skating might be the score the judges gave the participants, okay? That would be a different response variable. And so you have to come up with a response variable that's important to you. And there's usually several of these. So what you'd end up doing is you'd look at several analysis of variances using several different response variables, okay? Now, then you have to choose, well, what factors, levels, and what tests are you going to make? This goes back to define your problem again. Have you done a good job defining your problem? And these come out of your what you control, what you don't control. It come out of the understanding of the process. Okay. Then you choose your experimental design. We've talked about that, right? That's up front. We said there's, you know, random and fixed and so on and so forth. Now you go gather your data. Okay, because you have a plan and you're going to gather your data. You're going to gather it random. Remember, Sandy said, make sure you do this in random order. Make sure there's no bias to gathering the data. We've got an earlier talk where we discuss, you know, good data collection, right? And so you need to make sure that your data is not biased by something that you're doing as you're collecting it. Then you do the statistical analysis. As Sandy showed, you check your assumptions. Normality, randomness, you need to make sure of that. There's another provision where the variances of the different treatments need to be close to the same. We didn't show you that, but you need to check that too. Okay. Then you calculate the ANOVA, you make that neat little table, and you look at the answer. But then you have to come back again, and you got to say, so is this significant? I mean, you might see a statistical difference that makes no difference in reality. Okay? There's practical significance and there's statistical significance. They're not the same. So you go back to the top and you talk to the leadership. You say, is this a practical difference, right? And so that closes your whole thing. Now, you may need to iterate the experiments. You might have to go back and do it again, okay? Because you might find, well, we saw this here and we saw there, but we really think there's another factor that we need to include. Well, you go back and do it again, okay? Because when you start one of these things, you don't know what you don't know. And there's so much that you're unaware of, and you will learn more, and then you're going to go back and do it again. Okay, Sandy?
Oh, I wanted to add a couple things on this. Notice how many steps you go through before you get to your statistical analysis. My students always want to, be given the data and then get right to here, because that's the fun part, right? Is there a difference statistically? But notice again, this is knowledge of the process.
Yeah.
So you have to know the process to be able to do steps 1 through 5 before you can even get to the statistical analysis.
Mhm.
And then Doug alluded to this, but sometimes those decisions and recommendations aren't really super clear cut because it was close to being significant. There's these other factors. Say we then, the next step in our experiments were, okay, well, we think the ice has an impact.
Mhm.
You know, we think the order that the girls are skating has an impact. So there's a lot of other variables that then you can introduce. And again, we like as the engineering mindset to really be very definitive on this, but I'm always saying to my students, well, it depends.
Yeah.
You know, it really depends. It depends
Mhm.
upon the knowledge. It depends upon the factors. It depends upon how you ran your experiment and all of this.
Okay. Well said, Sandy. Thank you. So let's talk here briefly about common errors. Okay. Failure to check assumptions. We've talked about that as the data normally distributed. Our variances you're comparing are the same. And are your various observations independent, or does some of them depend on others? Misinterpreting p-values. Sandy was very clear about that. If p is low, HO must go. But you need to understand significance, like we said, significance statistically, significance practically. Okay. A small p-value does not necessarily mean that your effect was practically significant. All right. Inadequate sample size. Okay. Um, didn't get enough samples. Well, that's going to show a really wide, when we looked at the confidence intervals, that's going to show really wide. And you might not have enough samples to actually see what's going on. There's too much noise in the few you've got to see the signal that's buried in there. Okay. Ignoring outliers. If you got one value that's way off, why is it there? Okay. Is it significant? Or was there some glitch in the data collection? Okay. A glitch in the data collection process could mean you want to throw that outlier out. But if it's real, I mean, if it really happened, then you can't ignore it. And when you got small sample sizes, outliers would have a huge impact on this. All to do with that squared term in there. Okay, next one. Failure to, okay. Oh, ignoring covariance. Yeah, sorry about that. So things that are not independent are said to be covariance. If the result had something to do with, I'm not sure how your example plays into this, but if you had factors that were not independent, okay, they're one tied to the other, that might throw this off. Next slide.
Yeah, one thing that might be something is the experience level of the girls. That could really be
Oh, yeah.
correlated, co-varies with your results.
Yeah, if a relatively inexperienced skater was using what we think is the best skate, that would mess with the whole thing. Okay, good point. Okay, next. Multiple comparisons without adjustment. So if you keep testing and analyzing without adjusting, you can make a greater chance of a type 1 error. Okay, so you may need to get more data to do an additional comparison. All right. Another problem is misinterpreting non-significant results. So non-significant results do not mean that there's no effect. You might not just have enough samples to see. Okay. There's a number of other ways that goes wrong. Using one-way analysis of variance for repeated measures. Now we mentioned how one-way analysis of variance is when you get a factor, right? But what if you want to check, well, now I want to see this one against that one, and I want to see another one against, no, no, no. Now you're talking a different analysis. So one-way analysis of variance works within the limitations we've told you. If you've goofed and you've labeled some variables as dependent when they're independent, or worse yet, you measured something that is dependent and you're calling it independent. If you don't know your process well, this can happen. Okay? So mislabeling that and switching that around is going to really mess with, you won't have a valid study. You want to make sure that you report the effect sizes next to the p-values. If you don't, then the practicality of those differences gets muddied. Okay, so what was the actual difference? And what was the p-value? And maybe the actual difference, because the people, the leaders of the individual humans who are interpreting this can look at the actual values and they can say, oh, well, that's not practically significant. Yes, there's a difference, but we don't care. Okay. You know, post hoc power analysis. Now we're getting into the deep stuff. And again, it's probably a little bit beyond what we can cover here well. But a post hoc power analysis means you're going to look at the sample size. Was the sample size big enough to show this effect? Okay. And overfitting a model just says, if you got lots and lots of factors, too many factors, and you don't have a theory as to how they work together, you can end up making conclusions that are nonsense. And that's what overfitting does to you. So, in summary, ANOVA is a powerful statistical tool. It helps identify critical factors in our processes, again, within our limits. And it helps us assess whether treatment factors and level actually change our processes and our response variables, our outputs. Statistical tools aid us in the analysis, but as we've hit again and again, knowledge of the process is always important. So we have some references here. Yes, a book by Sandy is referenced. We want to tell you about the handbook of which this series has been discussing, the Certified Quality Process Analyst. Again, it's available from ASQ Press. Got the link down below there. And we have our contact information. And as Shobha said, you can send an email to me, doug@dcwoodconsulting.com, if you want a copy of the slides, a PDF copy, and I will be happy to send them along. So with that, oh yes, upcoming. So November 15th, we're back. We're going to talk about listening to the customer. This is the final webinar in our series here from CQPA. We will be talking about that again, 5 p.m. Central. You got a QR code that you can link to the registration for that. And December 6th, we have our friend Zach Gerard to come back. He's going to talk about examining quality 4.0. I'm sure you've heard of that. And it will be a really interesting talk. Zach is a well-read and well-studied individual. He'll have a good, interesting talk on that. So here's one more thing. We've not been telling you about this, but we've realized that YouTube now does closed captioning. But besides the closed captioning, it does translate. And so if the YouTube video is in English, you go into YouTube, go into our website right there, okay? And the QR code on the screen is our YouTube site for all of our videos. Not just Sandy's and mine, but all the QMD videos. You select your video, go to videos, then you click, stop the video if it's on autoplay, because it's probably going to come up and try to run. Then click the CC button. There's followed by the setting, a little wheel icon. you'll click on Subtitles/CC. Now there's another pop-up choice called Auto Translate. You click on this. Then you get a list of languages. Quite a range. We've got them from A to Z. You pick your language, and the closed captions will then be in your chosen language. From then on, in YouTube on your computer, it will use this until you reset it. So this means if you have friends who are their English is difficult for them, they can translate these talks, and the closed captions give them, okay, they're not perfect, but they're okay. It'll give them a gist of what's going on. So we're going to be adding this to our webinars from now on. One more thing, Sandy?
Sure. So I'm the Vice Chair of Publications for our Quality Management Division. So I'm putting a shameless plug in for articles. Any articles that you would like to share with the ASQ and Quality Management Division and all of our members aligned to the quality management body of knowledge, you can write an article for us, send it to me at sfurterer@gmail.com. Ideal article lengths around 1,500 to 2,000. That's not a hard and fast rule, especially because we are printing the next upcoming forum. If you would like a copy, send me an email. And this was the fall or the summer one, I think, or maybe it was the spring one. I think it was the spring one. Yeah, so that's a copy of what the cover looked like.
Okay. And I guess, oh yes, ASQ brings you all these things. And if you're a member, My ASQ is where you can go to find out more about all these things. So we'll hope to see you there. Thank you. And I guess, Shobha?
Yeah,
Back to
so
you.
I want to thank you both for this wonderful presentation, but we will get into the questions and answers that we have received. So let me stop recording and then go into that area.